Okay, so I heard you, good morning, and I heard you had a party yesterday, so it may not be easy to switch to back to gravity and extra dimensions after party, but okay, we'll try to do that. So let me summarize what we had in the what we learned in the previous lecture at the end. So as we said, we had two observers, and Bob and Alice, and so one was 4-dimensional observer and one was 5-dimensional. And so from the point of view of 5-dimensional observer, Bob, it was just a 5-dimensional Newton's law. It was a 5-dimensional graviton, just one particle, and or any other particle, and was this 5-dimensional graviton was mediating 5-dimensional Newton's law. Now, from the point of view of Alice, there was a tower of 4-dimensional gravitons, okay, tower of states. So this tower was either a continuum if the size, if extra dimension is non-compact, if the size is infinite, or if it's compactified, then it's a tower of, there is a mass gap, and then there is a discrete tower. And as we showed, what is happening is that essentially, so they are sort of, this tower is sort of, they are copies of each other. Their mass is quantized in units of inverse radius, okay? And because of this, at shorter distances you go, more particles are available. Sort of more and more of those particles become alive at short distances. At large distances, the particles, the members of this tower whose masses, whose Compton wavelengths are shorter than the distance that you are interested in, they do not matter, okay? They decouple. So they do not participate in mediating the force. Only the ones, at any given distance, only the particles whose Compton wavelengths are longer or comparable to that distance, those are the active ones that participate in the force, okay? Otherwise, the force at the Newtonian limit, in the Newtonian limit, the force is simply identical, mediated by those guys is identical, okay? So essentially, therefore, effectively what you do, when you go at shorter and shorter distances, you multiply the strength of the force, okay? So it's like you have, the way you can think about it is like you have a bunch of, so the heavier guys, they exactly mediate the force of the same strength, but they have shorter hands, okay? So their hands are shorter and shorter. So you have to go at short distances for that these guys be, so in that case they can be active, right? So in other words, the force that Alice or Bob, it doesn't matter, that they measure at any given distance, okay, is the same Newton's force, but n times stronger, okay? So this is n, where n is function of r, of a distance. N times stronger Newton's force, where n is the number of Kaluza-Klein states of this tower, members of this tower, whose masses, whose Compton wavelengths are larger than this given distance, okay? Whose masses, so this n is the number of those states whose masses are less than inverse distance, okay? The heavier ones do not participate. Now, this is why, inevitably, Alice sees, or whoever measures it, sees a stronger gravity at short distances, okay? Now, at large distances, this n gets reduced to 1. So once we go at a distance, so for the distances much larger, then the compactification reduces, because as we remember, we said that the first massive level, the mass is quantized in units of inverse radius. So first massive level is inverse r, inverse compactification radius. So this was the compactification radius, okay? And So therefore, once you go at the distance, which is much larger than the compactification radius, even the last guy decouples. And you are only left with the massless graviton, the normal massless guy at lowest energies. So that's why this n goes to 1. There is only one guy now available that mediates the force, and that's the usual normal graviton. And at short distances, the force multiplies. Okay? As I said, stop me anytime with questions, and if I don't see you, just shout. Okay, so this, so therefore, this tells us that effectively, this obviously, because of this effect, since gravity is now much stronger at shorter distances than it would naively be, what is happening is that the fundamental length scale at which gravity hits the maximal strength, the classical gravity, or fundamental length scale at which all the particles start becoming black holes, okay, after that, is of course much shorter, and there is a relation precisely following from this one, what I just wrote. So in other words, Alice will see that at short distances, the scale is not the Planck mass, actually. So let's take Planck square, is not the Newton's constant that she measures at large distances, okay, which will set this fundamental mass scale or the length scale. But actually, the mass scale gets reduced by n, okay, by square root of n. So in the other words, this is the relation between the fundamental mass scale and the Planck mass that she measures at distances, and they are related by number of Kaluza-Klein states. Okay. So let's introduce notation. So every time I will call, my notations will be that this m star will be always the scale where gravity becomes strong, so the fundamental length scale, which marks by default, which marks the energy scale above which elementary particles start becoming black holes. And I will introduce corresponding length scale, right, L star, which will be simply inverse m, okay, 1 over m star. Now, this is a general notation, okay? Now, in Einstein's theory, of course, these scales, if I have Einstein's theory with one particle species, whatever, okay, then of course this m star is the usual m Planck, and L star is the usual Planck length, okay? But this stops to be the case the moment you have this situation with more mediators of the force. Because more mediators of the force, they give stronger gravity. Okay? So now, let's evaluate this expression, okay? So in other words, in order to relate the fundamental Planck scale, fundamental scale and the Planck scale that we measure at large distances, okay, we need number of Kaluza-Klein states. What is the total number of Kaluza-Klein states available at that scale, okay? Now this is very easy, right? Why? Because as we said again, the number, what we need, so we start again in inverse, the tower is quantized, the masses go as n integer divided by r, okay? And we want to understand how many states are available from 0 to till energies m star, okay? M star energies. That's what we want to understand, right? And this is very easy. Why? Because the number of this total number of states here, the total number of states here, nkk, will be m star times r. Okay? Okay, everybody understands this, right? This is so therefore we can take this equation, use this and rewrite it, all right? Now again, so this equation had a very crystal clear meaning because all we said there are more mediators of the force, of course force is stronger, okay? That's it, there is no other meaning there, okay? Of course, these mediators, they open up at shorter and shorter distances, but eventually the number of mediators at this scale is given by some number, and therefore correspondingly the force is stronger. And then we just rewrote this in terms of these two scales of the compactification radius and the fundamental scale. Okay? Now, what does this expression tell us? This expression tells us that the larger is the compactification radius, there are more states available. Right? Why? Because it's obvious. Because I fix the interval, I make it larger. Because I'm making it larger, the spacing between masses becomes smaller and smaller, so I can pack them more tightly. Okay? So in other words, with larger r, they become more tightly packed. If I take r to infinity, I regain a continuum. Then I will have an infinite number of states. Okay? All right, so now as I said, let's use this, plug it here, and rewrite it. All right? So what do we get? We get, therefore, let me repeat it just for clarity, okay, that this was m star square times nkk. Then we use the fact that nkk is m star times r, and I plug it back here, okay? M Planck square, therefore, is m star square m star times r, okay? Now, okay, let's look at this expression, okay? Let's have a closer look at this expression, and let's see if we can interpret it in some other way, all right? The same thing, of course, physics is unchanged, we just want to interpret it in some other way. Whether we can understand it in some other way. Then, let's see what this factor n means when we write it in this way, okay? What is the meaning of this factor? This expression is nothing but a size of extra dimension, a volume, okay, measured in the units of fundamental length, right? Nothing else, right? Because, why? Because m star times r is same thing as r divided by L star, right? Because L star was a fundamental scale, the inverse length scale. And this is nothing but if I have a circle of size r and I measure it with a ruler whose length is L star, okay? So in other words, the meaning of this expression is that this is a volume of extra dimension, okay? And what this expression tells us is that bigger is the volume as measured in the fundamental units. I mean, of course, we always have to measure volume in some units. So I fixed fundamental scale because that's a constant, okay? It doesn't change with changing the size of extra dimension. It is whatever it is. So this tells you that when you increase extra dimension, the Planck scale increases. The Planck scale that we measure at large distances, okay? So this one increases. So in other words, gravity as measured, Newtonian gravity, as measured by an observer at large distances, okay, larger than the compactification scale, becomes weaker when you make extra dimensions large, okay? So now, why is this the case? Can we understand this in some other way? And the answer is yes. Of course, we can understand this very easily, why this happens. Was there a question? No. This is just the Gauss's law. Why? Remember, so what is Gauss's law? So first of all, how can we understand why forces, in general, forces, become weak with a distance, okay? We can understand it, as we said, I mean, we can understand it in different ways. We can understand it from exchanges, etc., but we can also understand it geometrically from the Gauss's law. Now, what Gauss is telling us is that if you want to understand force law, the way you have to think about force as if you have a source, and this source is literally a source of a flux, okay, of a flux lines. So what I have to think, for instance, if I have Earth, okay, what I have to think about, I have to think that this Earth is a source of flux lines, okay? Now, of course, in the spherical symmetric case, the flux goes symmetric. I don't know if I'm really drawing it in a very symmetric way, but anyway. So there is a flux coming out of the source. Now, the force, therefore, that you measure locally, okay, will be set by the density of the flux. Okay? So denser is the flux, stronger is the force. Okay? Now, then, to understand what is the force law, the only thing you have to impose is that flux is conserved. In other words, flux lines cannot break and cannot terminate at nowhere. They can only terminate on sources. Okay? Now, as soon as you impose this, the Newton's law and the Coulomb law automatically follows. Why? Because the point is that if the total flux is conserved, then I can always draw an imaginary sphere around the source, okay, or sphere of radius r. Okay, let's draw a sphere of radius r. All right. Now, and we know that the total flux is conserved. The flux is constant. So therefore, flux density, right? So what is the total flux is constant, right? This is flux. Okay. So this is constant. It cannot depend on the size of a sphere. But, therefore, flux density has to depend on the size of sphere. Okay? If I take a bigger sphere, flux density has to go down. The surface of a sphere in 3 dimensions is quadratic in the radius, right? So therefore, the surface of a sphere in 3 dimensions is quadratic in the radius. Therefore, flux density, which will be your force, Newtonian or Coulomb force, will go down as inverse square of psi, because this is constant. This is constant. Okay, so that's why forces, they always go as 1 over r square in 3 dimensions. The long-range forces, of course, I'm talking about. Inverse r square in 3 dimensions. Okay? Now, if I had more dimensions, so for instance, if I had 3 plus, so if I had 4 space dimensions, okay, which means that 5 dimensions in total, then the analogous sphere that I have to draw around, the imaginary sphere that I have to draw around the source, will have bigger dimensionality, cubic, right? So we'll go as r cubed. So for instance, in 5 dimensions, so this was 4-dimensional story, that's why 4-dimensional forces go like 1 over r square. Now, in 5 dimensions, the same story would be that r cubed times the 5-dimensional force should be constant, okay? And therefore, 5-dimensional force will go as 1 over r cubed. In other words, in more space dimensions you have available, forces, they change more rapidly with the distance, okay? They become much faster, stronger much faster, and they also spread out and become weaker much faster. So at large distances, so in 5-dimensional theory, at a given distance, the force diminishes with the distance much faster than in a 4-dimensional counterpart. Okay? Why? Because there's more space to spread. Flux has more space to spread. Okay? In 3 dimensions, there are only 2 dimensions on the surfaces to spread. In 4 space dimensions, there are 3 and so on. Okay? So generically, if I have, let me write this in different color. So if we had force in any 4 plus n dimensions, this would go as 1 over r square plus n, okay? This is the generic rule. Okay, very good. So now, let's come back to this story of why the Planck scale is measured, why Newton's constant is measured by Alice at large distances diminishes, okay? Well, we can understand this immediately from this Gauss's law, okay? No. So what are we dealing with is the following picture. We have a space, so we have 4 dimensions, so these are 4 dimensions, okay? Let's take like this, okay? So these are 4 dimensions, okay? Or whatever, 3 dimensions that we see. So this is 4-dimensional space, okay? And this is a 5th dimension, okay? Now here is Alice somewhere measuring this force, okay? So let's say now I have a gravitating source localized in these 5 dimensions, okay? So what is happening? Again, I can think in terms of Gauss's law, right? So there is a flux line. Well, let me draw this flux line in different color. So what is happening is that close to the source, if you are at a distance when r, the distance r that you measure gravity, is much smaller than the size of extra dimension, and this size is r, right? Then you are very close to the source. So because you are very close to the source, you don't really know whether space is compact or not. You don't know and you don't care. Okay? So close to the source, flux lines behave exactly the way they would behave in 5 dimensions. Okay? That's obvious. It's obvious, right? Because also in our universe, here in our universe, right, we have 3 dimensions. Now, 3 space dimensions. Now, we don't know. Some of those dimensions may be compact at a huge distance. So, for instance, it could be that some of the dimensions that we see, they are not infinite, but they are compact at the distances larger than today's Hubble size. Okay? But, of course, that will not affect measurements at short distances. At short distances, Gauss' law still will be 3-dimensional. It's exactly the same here. Okay? So, if you are close to the source, the Gauss' law that Alice will measure close to the source will be 5-dimensional, usual Gauss' law. Because flux cannot fill the walls of the space. Okay? However, once you go at large distances, what happens is that flux gets stabilized, right? Because flux lines, they can no longer spread. They can now only spread in 4 dimensions. There is no longer 5th dimension available for the spread out. Okay? And therefore, the flux line gets stabilized. Okay? After you go at the distances. So at the distances, much larger than the size of extra dimension. The spread out of the flux only goes into 4 dimensions. So Alice measures usual Newton's law. Okay? But with a Newton's constant, which of course will be set by the size of the dimension. Why? Because bigger is this dimension, less will be the density of the flux available in 4 dimensions, right? Obviously, right? Because, for instance, if I had a picture, which is obvious, because let's compare 2 pictures. If I have a picture like this, and I have flux lines spreading out like that, right? Whatever. And compare this with another picture when I have very small extra dimension. Now, obviously, the flux density will be higher, much higher. Okay? So in other words, depending on the size of extra dimension, if size is bigger, the corresponding spread out of the flux is bigger. That's why Newtonian gravity that she measures at large distances will be weaker, because flux spread out. Okay? This is exactly this relation. This one. The reason why Planck scale that she measures at infinity is sensitive to the size of extra dimension is precisely the spread out. Okay? So there is no difference really. Qualitatively, there is no difference in if we go to larger number of dimensions. Always is the same story. Always there is a relation between the Planck scale that you measure at distances larger than the compactification radius, 4-dimensional gravity, and the fundamental scale. The relation is always set by the effective volume of compactification as measured in fundamental units. Okay? The only difference is that if you have, instead of n dimensions, instead of 1 dimension, if you have d number of dimensions, so let's say we have number of dimensions is 4 plus d, then this factor here, which we had, m star times r, will have a power d here. That's the only difference, by obvious reasons, right? Because if dimensions are more, then volume is correspondingly has more dimensionality, right? That's the only difference. And exactly, if we translate it back in the language of Kaluza-Klein states, exactly we get the same relation. Equivalently, we can write it down in form of the Kaluza-Klein, number of Kaluza-Klein species. N, in form of N. This is N is number of Kaluza-Klein states in the theory. Okay. Okay, any questions about this so far? All right. Okay, so in other words, in this way we understood one way, okay, geometric way, how it could happen that these more messengers are available, okay, in the theory. So in other words, whenever you have high dimensional theory, this is a must. Whenever you have extra dimensions opening up at short distances, there are more messengers available of gravitational force, so therefore gravity becomes stronger, and that's an inevitability. The question, of course, the only question phenomenological is the scale. If we want to solve the hierarchy problem, if we want to say that this is precisely the mechanism which is behind the solution of the hierarchy problem, as we said, what we have to do, we have to identify m star with the TV scale. Because m star is the scale beyond which elementary particles become black holes. And so that has to be the TV scale, if we want to explain why electroweak scale is stable by this mechanism. Okay. Now, I don't see the clock actually. How much? Okay, whatever. Actually, it's interesting that now let's focus on this expression, and we will discover now a very interesting fact. Okay? So let's focus on this expression. And let's rewrite it actually, okay? Let's rewrite it. If I take this after doing a very smart mathematics, you just rewrite it in this way, that m star is equal to m Planck divided by square root of nkk, okay? So I have rewritten this in this way. Now, this simply tells you that the fundamental scale gets reduced by square root of number of messengers, okay? Of Kaluza-Klein states available in theory. In fact, it turns out, the amazing thing is that it turns out that this expression is very general. And this n here doesn't even have to be the number of necessary Kaluza-Klein states. In other words, in any theory, it turns out that in any theory in which you have n particle species, inevitably the scale where gravity becomes strong, or in other words, the fundamental length scale, is set by this expression, or correspondingly, L star is set by this expression, okay? N over m Planck. So this is the fundamental length scale, okay? So let's try to prove this, all right? That this is the case. Now, there are many different ways. Of course, unfortunately, I don't have time to discuss this, but there is one which is particularly interesting and nice. So let's try to prove this. So in other words, let's assume that we have, somebody gave you a theory. So Newtonian gravity, I mean normal Einsteinian gravity, you know nothing about extra dimensions. And somebody is telling you that in this theory, it's gravity, Einstein's gravity, plus there are n particle species available, okay, in this theory. So n particle species, let's call them some name, okay. I call them name, and they have, of course, they have an index, so that because they are different particle species. And this index is running from 1 to n, all right? The label. Okay. So in other words, for instance, example, in the standard model, we have particle species. So we have muons, electrons, neutrinos, etc., and they are different, okay? And you can label them. So now let's ask the following question. Given this fact, what can I say about, and given this fact, and given that I know that I have Einsteinian gravity at some large distances, what can I say about the fundamental scale of the theory? Okay? Now remember, we were saying that in Einstein's gravity, when we have one particle, let's say around, let's say graviton, there was an absolute limit to the size of a length scale which you could probe in that theory, right? And this absolute limit was the Planck length. Now you see that now in this theory what we will get is that the absolute limit is not the Planck length, the inverse of the Planck scale, but actually is longer, square root of n times longer. So in other words, the length scale that you get is square root of n times the Planck length, right? L Planck. And we want to prove this, right? Now let's try to prove this. So what it means to have, first of all, let's ask the following question. So for a physicist, what it means to have n different particle species, okay, in the theory. So to have n particle species means that you can label them. If you cannot label them, then they are not different species, because there should be some experiment in principle available which will give you a possibility to distinguish them. I mean, that's what we are trying to do at LHC, right? That's why we have these huge detectors, because eventually we want to tag, we want to identify particles that we get, right? If you cannot identify them, in principle, then they are not different particles, okay? So, in other words, the length scale at which you stop being able to identify your particles is automatically the size of your black box. You can no longer probe your physics behind that scale, okay? So, now, therefore, the fact that somebody tells you that there are n species available in your theory means that you are able to probe them and distinguish them, okay? So now let's try to understand how we are normally distinguishing particle species experimentally. Now, experimentally, what is the story? So first of all, given the fact that you can label this particle species, right? So label of a species is a form of an information, right? So using particles, for instance, we can exchange messages. I don't know, for instance, if I have n particles and I send you one flavor, we can agree that this means something, right? So for instance, I send you a first flavor, and so this means that we have a party tonight or something. I'll send you a second flavor, this means that I'm away. So it's a message, right? So which you can decode. Once you identify this particle, you can read my message, okay? So now, what is the typical decoder? How you identify particles? So, of course, the detector, always it has pixels, right? So it has a sort of unit, a pixel. And you have, the point is, so let's consider the following story. So here is my pixel, a detector, okay? And here is a particle of an unknown label, okay? So there are n of them. Somebody is sending us an unknown label, particle with unknown label. We have to identify the label. We have to identify the particle. So this pixel has to contain sample of at least all of these n species. Okay? Why? Because you have a sample of n of those, and then you compare what this guy does. Okay? How it interacts. Right? So this means that in this pixel, I have all the species available. Sample of all n species. Now, let's say the size of this pixel is L, okay? Now, the question, therefore, about the fundamental scale is that how small you can make your pixel, right? Because once you hit certain limitation that you cannot make your pixel smaller, that's where you stop. That's what is the size of your black box, okay? This means that that's the absolute length scale on which you can decode this information, right? So in other words, the typical experiment has this form. This guy comes, interacts with the pixel, and then goes out, and then you read the result. Okay. So now the thing is that the point is that if in an imaginary world without gravity, what is interesting is that there is no limit to the smallness of this pixel. So without gravity, you could have, in principle, of course there is a technical issue, but in principle you can store information arbitrarily fast and decode it arbitrarily fast. The limitation comes from gravity. The reason, because you have gravity, okay? Why? The reason is the following, okay? So, to localize a particle, so let's rewrite it in more So from the point of view of quantum mechanical way is that I have this pixel, size of this pixel, and then I have wave functions of these particles somehow localized in this pixel, okay? Right? So I'm localizing these wave functions in the box. Now, as you know very well, the localization of a wave function or of a particle is never for free. You need energy to do it, okay? So in other words, the device or pixel or whatever that localizes the particle, it has to wait. It has to carry certain energy, okay? So at least to localize one bit of information or one particle, at least you need energy 1 over L. To localize n, so you need energy, which is, so the energy of n particles localized would be at least or larger than n over L, okay? Very good. So this is the energy, or this is the mass, okay? So in other words, this is the mass of a pixel. Okay? Now, so therefore, now the point is that now we have a pixel which has certain mass, and we have a pixel which has certain size. And the question is, now we want to make this pixel smaller and smaller. But what we notice is that if we want to keep the same number of species, being able to distinguish among the same number of species, while making this pixel smaller and smaller, we inevitably increase its mass, okay? So we have something that we decrease the size and increase the mass, okay? Now, of course, this rings a bell because eventually this thing will collapse into a black hole, okay? Continuing decreasing the mass, decreasing the size and increasing the mass, eventually you hit the point where the whole thing collapses into a black hole. So where is this place? Let's understand where is this place, okay? In other words, let's compute the Schwarzschild radius of this object, okay? Mass of the pixel. It's very easy. So the Schwarzschild radius of a pixel, okay, let's call it R of a pixel, is, well, it's, okay, let me, well, it's twice Newton's constant times mass of the pixel, right? Which is effectively m pixel divided by m Planck square, okay? Or, using the mass of the pixel, this is n divided by L m Planck square, okay? So this is the Schwarzschild radius of a pixel. Now, you see that we obtained a relation between the Schwarzschild radius of a pixel and the size of a pixel. And so the obvious point is that the pixel should be, in order not to collapse into a black hole, the pixel should be larger than its own Schwarzschild radius, okay? So in other words, which means that L has to be larger than its own, so in other words, not to be a black hole, not black hole, this implies that L is larger than R pixel, larger or equal. When it's equal, it's already a black hole, okay? So, which gives you an equation of the critical size, which is, let's use this, right? So the equation is that L, the critical L, let me call it L star, is when n, well, let me call some other name, okay? Let me call L pixel, the critical, is n L pixel m Planck square, okay? Now solving, in other words, the size of the pixel has to be larger or equal to this, okay? Which means that, which trivially means that L pixel has to be larger or equal to square root of n times the Planck length. So we got exactly that length scale that we were talking about, remember? So in other words, this tells you that just from the fact that you want to be able to distinguish particles, if you have many particles, automatically there is a limiting scale in your theory. There is a black size of a black box. And at that point you should stop, okay? Which means that every time you have many degrees of freedom, many particles, gravity has to do something by consistency to accommodate you a strong gravity at short distances, okay? And in fact, vice versa. So, because this is the same L star scale that we got. Now, in this concrete example of 5 dimensions, right, you see what happened, right? In that 5-dimensional example, this n was simply number of Kaluza-Klein states. But this tells you that this expression is more general. So, in other words, of course, I mean, every object has a Schwarzschild radius, and so it has to be bigger than its own Schwarzschild radius to be recognizable, okay? The Schwarzschild radius of the Earth is approximately 1 centimeter. So you can tell that this is an Earth as long as it stays larger than its Schwarzschild radius. Once it crosses it, there is no way to recognize it, because all the memory that it was Earth is lost. End result will be 1 centimeter black hole. And will be no difference whatsoever whether you got this 1 centimeter black hole from the Earth or from any other planet of the same mass or any other object of the same mass, okay? So, this is, in other words, this limits the size of anything that you can recognize, which is not a black hole, okay? Any questions about this? Anybody sees this time? What time is there on the clock? It's 10? 5 to 10, right? We have 5 minutes, okay. All right. Now, let me discuss now briefly some consequences of this idea, okay? So, in other words, there are consequences. If strong gravity is responsible for solving the hierarchy problem, then there is an immediate prediction that at that scale you should see strong gravity effects. Now, what are the strong gravity effects? Now, first, I will start with first, which is from this discussion, it's obvious that it is model independent. What is the story? The story is that if your fundamental scale is L star and M star, right, the mass scale, we said that any particle, any elementary particle heavier than M star is a black hole, okay? And then heavier guys become quasi-classical black holes, okay? Which means that you should start eventually in the collision of particles. Eventually, you should be able to form black holes, which then, with the energy, will become quasi-classical in the particle collisions, okay? Now, in other words, so let's take Einstein's theory, okay? So in Einstein's theory, if we don't care about anything, any of this, let's say we have one particle, E plus, let's take electron, okay? So, or whatever, any other particle. Let's say in Einstein's theory, we do a scattering experiment, okay? We collide a particle and then an antiparticle, okay? With some impact parameter, certain impact parameter, okay? Some impact parameter R, okay? And certain mass energy E. So, what is happening? If energy is much less than the Planckian energy, right? So first energy is much less than the Planckian energy, okay? So gravity doesn't play much role in the scattering. So most of the scattering happens because of other exchange of other forces. For instance, if this is E plus E minus, most of the time you exchange, with the highest probability, you exchange photons, okay? Now, suppose we suppose we increase the center of mass energy in the collision, and correspondingly we try to decrease the impact parameter, okay? So we aim better, okay, with higher energy. So eventually gravity becomes stronger and stronger, okay? Contribution from gravity is stronger and stronger. Then we hit the Planck scale. After this point, if you start increasing energy further, as we explained, what you get is that you get a black hole which with high energy will become more and more classical. So in other words, if we collide E plus E minus or whatever with an impact parameter which is less than 3 kilometers, for instance, okay? and the energy is the solar mass, the outcome will be that we form a solar mass black hole. So in other words, the high end of the energy collision in gravity is, we anticipate it pretty well. We know that what will be is classical black hole formation. Okay? They will dominate the cross section at very high energy. So now, coming back to this story with TV gravity, the story will be very similar, except that everything will happen at this scale m star, which, if this is the source for the stabilizing hierarchy, is a TV scale. So then, in this case, LHC has a chance to observe a black hole formation in the particle collisions, okay? In the particle collision experiments. Now, the thing is that now we can ask the following question, okay? What will happen with these black holes that we form at LHC? How can we understand that they are black holes, really? Now, of course, when people talk about black holes, they have in mind big classical objects, okay? Now, inevitably, we know that the black holes which you start forming at threshold, they look nothing like big, fat, classical black holes, okay, that we see in astrophysics. The first ones that you can potentially call something like black holes will be very much like particles, okay, because they will decay very rapidly, and they simply will not have time to be democratic into the to decay into different particle species, etc. So in other words, the small black holes, the smallest ones, they carry hair, okay? As and this goes in sharp contrast with the big ones. In other words, the qualitative picture, which I'll continue briefly in the next lecture, is that the first black holes will be produced, they will carry hair, and if you are able to increase energy in the collision, you produce heavier ones, they will lose the hair. So the hair will become less and less. Eventually, you can produce a black hole which has no hair and which is classical. Of course, the LHC will not go up to those energies. So at best, it will probe the threshold and maybe something about the threshold of black hole production. But still, if this is if we are so lucky, this will be an extraordinary event, of course. Anyway, so let me stop here, and then we continue next lecture. So we have in 15 minutes or something, right? Next lecture. Okay.